Okay, we're back with wind. Okay, this is the second part of the wind video. Might even be a third part, not sure. We'll see how things go. But in the earlier part of the video, or the first video, one of the key concepts was this idea of, well, actually before we even got to this, that the reason we have wind in the first place is because of differences in heating. Some areas of the Earth get hotter than others, and that causes changes in density, and because of that, then we have wind trying to balance everything out. And the wind is bringing, trying to even out the temperature. So here we have two particular types of breezes. We have the sea breeze and the land breeze. And again, the warm air rises up over land during the daytime because the air heats up faster than the water. Water has that high specific heat. It doesn't heat up very easily. Then the air spreads out in both directions. It begins to cool. It's over that cool ocean air, or cool ocean water rather. It sinks, and we have a convection cycle, just like we would have in the heat in the classroom or the outer core of the planet. At night, the process reverses, and we end up with what's called a land breeze. In this case, the water is warm relative to the land. The land cools off a lot at night. The water stays relatively warm. And it's not that the water really changes temperature, it's just that the land changes temperature much more than the water does. And when this happens, we have the reverse effect, which we call a land breeze. At night, the air is moving from the land to the water. So, that brings us to wind direction. Wind always blows from regions of high pressure to regions of low pressure. Okay, so we're always trying to balance things out. And wind always blows from high to low pressure. Now we also have this effect on our planet called the Coriolis Effect. And it's called an effect because it's more an apparent effect than a real phenomenon. And this Coriolis effect has to do with Earth's rotation. If Earth did not rotate, then we wouldn't have the Coriolis effect at all. Now, I think what we'll do is look at the Coriolis effect in more detail in another video. But for now, I'll just kind of make a little side note about Coriolis. Basically, the concept of the Coriolis effect is if we have the Earth, and I'll try to draw a circle as best I can. Let's say that's the Earth. And let's say here's the equator. And for example, let's just pretend that you have a large cannon down at the equator. And this little rectangle will represent the cannon. And let's say you're trying to hit location X with your cannonball. Because of the Coriolis effect, when you fire your cannon, are not going to hit location X. Your cannonball is actually not going to travel in a straight line at all. This is kind of strange. It actually takes a curved path. And it's not so much that the cannonball is curving through the air, it's that Earth rotates under the cannonball. And because the Earth is rotating under the cannonball isn't going to hit where you aim. You know, if you aim at this X here, you're not going to make it. Your cannonball is going to be in the air for a little while, and in the meantime, Earth rotates under the cannonball, and the cannonball is going to impact somewhere off to the side. This is the same phenomenon we see with the wind, this concept of Coriolis, and I'll look for some YouTube videos that I think will explain this pretty well. And when we get back to school together, there's a very simple demonstration I can show you this with a classroom globe, but I just don't happen to have a classroom globe here at home. So anyway, the idea with the Coriolis effect is things are going to appear to be deflected to the right in the northern hemisphere. That should be to the right. So in the northern hemisphere, wind or cannonballs are going to get deflected to the right. If you really want to hit where you're intending, you need to take into account Earth's rotation. The military is very good at this. They know how quickly the Earth rotates, and they factor that into their artillery firings and so on. In the southern hemisphere, objects are going to get deflected to the left. It's the opposite. So in the southern hemisphere, our cannonball is going to get deflected to the left. And that's something that I could easily prove to you with a classroom globe. I just don't have one here. It might seem kind of counterintuitive that it's opposite, but for now, just take my word for it. If you really want the proof, I can do that for you when we get back together. Okay, so anyway, in the northern hemisphere, wind gets deflected to the right, just like the cannonball does. And in the southern hemisphere, wind gets deflected to the left. Now, if we look at high pressure, and here's low pressure, we have wind going from high to low pressure. And when we have an area of low pressure, wind is going to try to even things out, and it's going to move into the center of that low pressure from all directions. High pressure is going to be the opposite. In a high pressure situation, the wind is going to be moving out in all directions. If the center of your high pressure is here, there's nowhere else for the wind to go except away from the high pressure. If your center of your low pressure is here, the wind has nowhere to go but towards the center. Now, in addition to this, and remember this is a map view or a top view, we're looking down from above, we have this Coriolis effect factored in there as well. And with the Coriolis effect, in the northern hemisphere, the winds get deflected to the right. So instead of the wind just moving straight out from the high pressure, it curves to the right, like this. Which is actually clockwise rotation. That was something that we talked about a while ago. High pressure rotates clockwise, and this is why. When the wind moves out from the high pressure, it's going to get deflected to the right. And that right deflection for all of the wind essentially is a clockwise flow. With low pressure, we have wind moving in towards the center. And if we imagine ourselves facing the direction of the arrow, the right is going to be this way. And on this one, it's going to be this way, and then this way, and then this way. That might be kind of an awkward way of drawing this, but the point is, now our flow is counterclockwise. And we have counterclockwise flow of air around a low pressure system. If we were to look at the same situation from a side view, we've got our high pressure here, we have our low pressure over here, and the wind is going to go from your high to your low pressure, trying to balance everything out. We're going to have wind getting pulled into the low pressure from over Boston. We're going to have the wind from the high pressure moving outward like that. And if we were looking at a true side view of the entire atmosphere, we would see air sinking over the high pressure, coming together like this and sinking. And then over the low pressure, air is going to be rising. And this is really important. This rising air is part of cloud formation. We were talking about that in some of the earlier videos that I posted. We get clouds forming when air is rising. When air is sinking, you're going to have no clouds. Air is warming. Air warms. Remember, in order to have a cloud, air has to cool. This is why we have clouds over low pressure systems. And this is why low pressure systems are associated with storms, while high pressure is associated with good sunny weather. Sinking air is opposite what you need to form clouds. And that's why we don't see clouds in high pressure, but we see clouds with low pressure. Now, there's the term cyclone and anticyclone. A cyclone is just another term for a low pressure system. It's not a tornado or a twister. Sometimes people think that. It's not exactly a tornado or twister. Cyclone just means low pressure, essentially. Anticyclone means high pressure. So around a high pressure, we would have clockwise flow. And around low pressure, we would have counter-clockwise flow. So for high pressure, it's clockwise and out. For low pressure, we have counterclockwise rotation, and it's going to be going inward. Kind of like this. So we've got the flow being counterclockwise and in. Inward towards the center of the low pressure. On high pressure, clockwise and out. So let's just summarize this, and then we'll stop for this video. So in a high pressure system, winds move clockwise and out. And in low pressure, they move counterclockwise and in. Now, on the large weather patterns lab, this is a similar exercise. It says on the map on page 28, that's probably a different page, but extend the shaft of the station model, draw the head of the arrow to show the direction the wind is blowing, draw larger arrows to show general direction of airflow. This is exactly what the lab asked you to do. So if we go back to, I think it was, our air pressure map from one of the other videos. Okay, we already did this. We've got the arrows extending through the shafts, showing the direction of flow. And with high pressure, it's moving outward and clockwise. Low pressure, it's moving inward and counterclockwise. Okay, why don't we stop here, and then we'll do one more video on wind, and that will be it for wind. Okay, so I'll post another video about wind speed and what's called pressure gradient. Okay, so that's it for now, and we'll do a part 3 in a few minutes.